Hello, everyone. My name is Evan Yu, and I'm the author of Vue.js, and really happy to be here. I was actually invited last year, but had some schedule conflicts, and I'm really excited to be here this year. So today's talk is about compile time optimization in JavaScript applications. As I was watching Igor's talk, I realized there's actually a pretty good synergy between the talks, because we're going to be mentioning some of the concepts that Igor leveraged in his demo. And this talk is not going to be specifically about Vue, but there will be some Vue-specific parts, just to be clear about it. OK, so front end used to have no build steps when we first started. Everything is just plug and play. You drop the script into a page, and you open the page in the browser, and things start working. But today, right, compilation or a build step is an essential part of our workflow now. We have Babel, the JavaScript compilation infrastructure. We have bundlers like Webpack, Rollup. We have compile-to-JS languages like CoffeeScript, TypeScript, and even Reason or Elm also compile to JavaScript. We have CSS preprocessors like Sass-less, and also PostCSS, which is more like the compiler infrastructure for CSS. So we have all of these tools that we leverage today. But I want to take a step back and think about, like, in the early days, we've actually been using compilation optimizations way before these tools. Okay? But before that, let's think about what compiler really is. This is not the compiler in the strict, back in the C days. We're just talking about it in a very cross-language term. As a cross-language term, really, it's just something that takes the source code and emits target code, whether it's compiled JavaScript or binary code. We don't really care. And the process usually involves, parsing the source code into an AST, and then manipulate it, transform it in some way, and eventually generating the target code. And in this AST transformation phase, this is our opportunity to apply a lot of interesting transforms, analyzing the structure of the AST, and do all kinds of possible optimizations, right? And one of the earliest way we've leveraged compile time optimizations is just minifiers. And if you think about minifiers are essentially compilers, right? They take some input, your source code, and then emit the minified code. And in doing that, it usually requires properly parsing your JavaScript, understanding the structure of your code, and then applying the proper optimizations. If we look at some of the main, most prominent minifiers, we have Closure Compiler, Uglify.js, Babili, I think it's renamed to Babel Minify now, and Butternut, which is the minifier written by Rich Harris, who basically writes an alternative implementation of everything. And if you think about those, Closure Compiler basically says in its name it's a compiler. Uglify.js has its own implementation of a parser, its AST format, its codegen. Babel Minify is built on top of Babel, which is a compiler infrastructure. Butternut has a similar architecture to Buble, the lightweight ES 2015 compiler, which is also a compiler. So we've been using compile time optimizations long before we realized it. But it's only since the arrival of these compiler infrastructure tools like Babel and PostCSS, we started doing more interesting things in this area in recent years. And we'll explore that in the rest of this talk. So first thing, so going along with the minifier theme, we're trying to make our code slimmer. This is a unique problem for browser code, because we really care about how much code we eventually send to the client to save bandwidth, make pages load faster. So tree shaking is one important thing, which Igor already mentioned in his talk. And specifically, tree shaking is implemented by doing module scope hoisting. Right? So if we look at ES modules, we have a main.js and 2 files that's being imported, and we are calling the code in the main.js. Right? And with module scope hoisting, we'll just put them inside the same file. So without module scope hoisting, if we look at the code generated by Browserify or Webpack without the module concatenation plugin, you'll see that each module is wrapped in a function scope, which makes it difficult for minifiers to analyze what things can actually be dropped. However, with module scope hoisting or module concatenation, everything is put in the same scope. This is what Rollup does by default and what Webpack does if you enable the opt-in into the module concatenation plugin. And the cool part is when we comment out the code that actually uses these imports, now the minifier is able to infer that things are not actually used and able to just shake them. And we end up with nothing if we don't actually use anything, right? So that's tree shaking, and that's also a form of compile time optimization. And it's the collaborative work of our bundlers, which is smart enough to infer the relationship of your modules and variables, and the minifiers, which takes the output by the module bundler and then perform its own optimizations. Okay, so yeah, in Webpack you need to opt into the module concatenation plugin to get this behavior. And so that was about making code smaller. Then let's think about template compilation, right? So this is loosely related to React in some way because we also need to compile JSX into raw JavaScript, but it's more common for other frameworks which leverages templates such as Vue, Angular, Svelte, or Ember. All have templates, and they all need compilers to compile these templates. And the strategy each of these frameworks take are slightly different. We'll briefly go through each of them, but in terms of the detailed optimization techniques, we'll be focusing a bit more on Vue in the later part of this talk. So this is more like a higher level overview of what each framework is doing, right? So for Vue, many of you probably know, in Vue 2.0, we rewrote the rendering layer, and we essentially compile all Vue templates into render functions. And the underlying, so once compiling to render functions, it goes into the similar domain of virtual DOM, rendering and diffing, similar to React and all the virtual DOM inspired libraries. And during this template to render function compile phase, we're actually, because we get an AST of the template, we're actually able to apply some pretty interesting optimizations, which we'll talk about later. In Angular, so this is a screenshot taken from a talk at NGConf on the optimizations brought into the Angular compiler in Angular 4. So if you look at the comparison, on the right you see the code generated by Angular 2, and on the left you see the code generated by Angular 4. So Angular 2 takes a more direct style where you directly generate all the code that imperatively creates the elements and binds the directives and performs the updates. In Angular 4, it's optimized by extracting some of the more repetitive parts into the runtime, into the shared runtime, and expose these reusable functions that's used in the generated code. So this was a big improvement because it greatly reduced the final bundle size of Angular applications without changing anything in terms of user-written code. The template is the same, but just because we improve the compiler, Angular is able to greatly improve the performance. And Svelte is also a great idea. In case you're not familiar with it, Svelte is also written by Rich Harris, who is the author of Rolla, Buble, and other things. So Svelte also uses templates, but it takes a slightly different strategy by compiling the templates into more direct DOM manipulations with optim runtime. So if you look at the code, it actually looks pretty similar to the version 2 code that's generated by Angular. But the big unique thing about Svelte is its runtime code is pretty much, the majority of its runtime code is opt-in. So if you create a Hello World Svelte app, the bundled runtime is only like less than 200 lines of code. It only bundles the necessary runtime code when your template actually uses a certain feature. So this results in very small default bundles because it uses a very specific style of code generation. And then there's Glimmer, which is also pretty unique in the compilation strategy by compiling handlebars templates into opcodes. So these opcodes are then feed into the runtime, which is called Glimmer VM, which Tom Dale will actually be talking about it in more details tomorrow. But the most unique thing about Glimmer opcodes is that they are binary friendly. So it's possible to generate the opcodes as binary artifacts at compile time, and then you can just directly fetch them as a binary stream and instantiate them as a typed array, and which gets rid of a lot of the parsing and evaluation if you're using a raw JavaScript or JSON format. It's also pretty WebAssembly friendly. Okay, so these are some of the common strategies, different styles of compilation, template compilation, different frameworks. But the common theme among them is also AOT versus JIT, ahead of time versus just in time. So a lot of frameworks in the past, for example, Handlebars and Vue version 1, and Angular 1 also, most of them perform the template compilation directly in the browser. So the cost of parsing the compiler, analyzing the structure, and generating code has to be performed on the client. It takes up the time to interactive in a user application. So the natural step is, if we already have a build step, we definitely should move this template compilation step to the build time to avoid the runtime cost. So this is the default. I believe Angular already moved to AOT by default. Correct me if I'm wrong. If you use the Vue CLI generate templates, we use AOT by default as well. I believe if you scaffold an app with Ember with latest Glimmer, it's AOT by default as well. So this is a common thing that's implemented by most frameworks. And I believe Svelte doesn't even have a JIT option. So you have to do AOT compilation. And the next interesting thing we can do by having a compilation step is scope CSS simulation. So this is not technically a performance optimization, but more like a developer experience optimization or a developer pattern optimization, right? So the rise of CSS in JS was so CSS in JS obviously have some unique advantages in certain areas due to its closer relationship to JavaScript. But the prime reason that CSS.js came up as a solution was to solve the component styling problem. We want to limit CSS to our component as a boundary, and plain CSS was a nightmare to maintain because of the default cascading behavior. Right? So in Angular 2, in Vue, in Svelte, we all have a similar strategy by simulating scope CSS during the compilation step. So we can, because our styles and our component templates are naturally connected, or they are either co-loaded in a single file component, or they are somewhat imported, have a module dependency relationship, the compiler is able to infer the relationship between the template and the CSS in order to rewrite both at the same time, so that the template and the CSS are perfectly, so the template is rewritten with extra attributes hooked onto each element, and the CSS has its selectors rewritten to be more specified. So the CSS will be scoped to only the elements of the current component. And this simulation, this almost perfectly simulates what we would expect in a shadow DOM scope CSS that's supported natively, but it doesn't require any polyfills, and it works all the way back to IE9, which is pretty nice. Even in CSS in JS land, we also have solutions like Style.jsx by Zeit, which is somewhat inspired by the scope CSS implementation used in Angular, Vue, and Svelte that allows you to embed a CSS string in your JavaScript and then use a Babel plugin to analyze and transform the CSS at compilation time. It's even able to support Sass or other preprocessors in CSS in JS by adding plugins to the Babel plugins. So plugins for plugins for plugins. Because we have compilers, why not? Okay, so the simulation pretty much looks like this. So this is a view-specific implementation. If we have a class equals red, we will add a unique data attribute to the element, and the selector will be rewritten with the specific attribute selector to make it only match this specific element. So we've talked a lot about analyzing static stuff like templates and CSS, but how about React, right? So the thing about React is almost all JavaScript. You put everything in JavaScript. JSX is JavaScript. CSS in JS is JavaScript. And we have Babel for JavaScript, right? Babel is the compiler infrastructure for JavaScript, which is why it's natural to perform all of these similar compile time optimizations for React using Babel plugins. And there is, so James Kyle has this great Babel React Optimize plugin, which performs a bunch of common optimization strategies by default. We're not going to dig into all of them, but the most prominent one, and a lot of you probably know about, is hoisting static elements, right? The culprit of virtual DOM is on every render, we are recreating all of these virtual nodes. And a common problem is if you have a large chunk of nodes that are just static, they don't have any dynamic bindings to them, we're still comparing them and trying to diff them on subsequent re-renders. So if we're able to detect such static trees at compile time, before we even ship things to the browser, we're able to just transform the code and hoist the element out into a constant, right? So this idea came up as early as in like February 2015, which is like more than 2 years ago, if you think about it, how fast time moves in JavaScript land. And obviously, we have similar optimizations in all the template-based solutions as well. And to be, so this is not bashing React, but to be honest, because of the dynamic nature of JavaScript, it's usually a bit more difficult to do this type of optimizations because JavaScript is too dynamic. So there are a lot fewer assumptions you can make, and there are more cases that you have to bail out or de-opt. Basically, you give up, saying like this part we cannot analyze, we cannot optimize it. So to quote from Tom Dale, what we call web frameworks are transforming from runtime libraries into optimizing compilers. And I think we're going to see more of that trend coming up. OK, so on top of, so going with that theme, frameworks becoming compilers. Right? So there are a bunch of meta optimizations that's even outside of the template or style scope. There are application level optimizations that are somewhat cross-framework. So Webpack code splitting. Igor mentioned how it can help us improve performance. And in fact, it's also a category of compile time optimizations because we're using the ES dynamic import syntax as a compilation hint given to Webpack. So whenever Webpack's parser sees the dynamic import syntax, it will convert it into a AJAX request, which fetches the content. It also splits your output code in 2 pieces. And then it includes this runtime piece of code that is responsible for fetching the asynchronous part and returning it to you as a promise. And this is the usage combined with Vue's async components. And this is essentially how you would just turn a Vue component into an asynchronously fetched one if you use Webpack. We also have some great ideas coming from Relay Modern. So Relay Modern rewrite was mostly about performance. In order to improve performance, their conclusion was that they need to do more at compile time, right? So what Relay Modern does is it pre-compiles GraphQL queries and schemas and generates runtime artifacts and types that can be fed into the application at runtime. But originally, if this compilation phase needs to be performed at runtime, it just takes too much time, is not even cost effective. But if you perform it at compile time, it becomes a complete gain, a pure gain. So which is, this is a great idea. So although it results in slightly more complex deployment operations, still the performance gain greatly outweighs this trade-off. And then we have Prepack, right? This is like meta level optimization. You just give it your JavaScript and turns your JavaScript into more optimized JavaScript by doing partial evaluation, right? So the strategy it takes is it'll essentially run whatever code is possible in your source code and try to produce the code that results in the same side effect, right? So if you have a Fibonacci function and you call, so the code on the left, if we look at it, the only side effect, the eventual side effect that we're producing for the whole code bundle is the global variable x. And that's the only side effect this whole bundle is producing. So Prepack is able to run your code and draw the conclusion that the only side effect we really care about is the value of x. So it results in the code on the right, which is pretty smart. But it also does things like for loop unrolling, which turns your for loops into sequential imperative calls. But sometimes it's just it's a trade-off between code size and execution speed. So Prepack still has some improvements to do in that aspect, but still it shows great potential in the future optimization of our JavaScript code. And it's not bound to any sort of framework implementation. You can apply it to any code that you write. And then there's a proof of concept which 3.1, Sunil Pai, he shared this idea at React Europe earlier this year, I believe. So I'd recommend people checking it out because I think it's a pretty interesting idea. Unfortunately, this is just a proof of concept. I don't think he continued working on it. But the idea is we use ES decorators in the source code as compiler optimization hints. So, for example, the compiler is able to detect parts of the app that says, oh, this part, I need to, for example, during server-side rendering, I need to just skip it and don't render it on the client, or this part needs to be code splitted. So there are all kinds of ideas. You have these interesting decorators that's in your code that turns your turns your eventual output into completely different things. And I think this is a very interesting direction. And if done correctly, this can also be done in a framework agnostic fashion, which I believe was Sunil's original vision. All right, so now time for some Vue-specific stuff. So we mentioned that Vue compiles templates into render functions, and we, in fact, do a lot of interesting things during that phase. The first is, obviously, hoiting static trees. We detect static content in your templates and take them out, stored somewhere as constants. And inside our render function, we simply return the same node over and over again. And these nodes are considered static, and during subsequent patches, we don't do anything about them. We see, oh, these are the same nodes, we just skip them. Skipping static bindings. If you have a class binding that is a plain string, it's different. It's put into a different namespace compared to dynamic class bindings. And so all the static attributes and static classes don't even need to go through the different phase if we are performing things correctly. And then there's a thing called skipping children array normalization. So if you use JSX or render functions, we know that when you can return an array as children of another element. So the result is each virtual element can have a children array that has nested arrays inside of it. So it is necessary for the virtual DOM runtime to flatten the children array in order to perform proper diffing. Or if you don't flatten it, then you have to cater for the nested array scenarios in your diffing algorithm, which results in also results in runtime cost. So in Vue, we also have this problem. Like, for example, if you use a v-for loop inside the children of the UL, you will have a children array with nested arrays by default, and we will need to flatten it. And also because Vue's the JSX syntax or the hyperscript syntax for Vue render functions is pretty flexible. So you can pass primitive values, such as strings and numbers, as children into the render function call. So all of these things needs to be normalized into actual virtual nodes before we pass it to the diffing algorithm. So the thing we do in the template compiler is we will detect cases where we know that we generate code that basically ensures that the children of every element are already a flat array of virtual nodes. So there will be no edge cases where you need to flatten nested arrays or turn primitives into virtual nodes. Everything is directly generated as pre-normalized values. So this allows our runtime to completely skip the normalization phase. And so as you can see on the right, so this is not the exact code that we're generating, but it kind of gives you an idea. So we pass in additional arguments into the render function call, the create element call, telling it that the children is pre-normalized. So at runtime, we don't need to do anything about it. And for large lists, this significantly improves performance, especially on very fast re-renders. And for server-side rendering, right? So virtual DOM-based solutions can do server-side rendering, but usually needs to, because of the nature of virtual DOM, you need to first create the virtual DOM tree in memory before you can serialize it into JavaScript, serialize it into strings. This is one of the primary reasons why virtual DOM-based server-side rendering is typically slower than pure string-based templating engines. Compared to plain string templating engines or frameworks that perform server-side rendering using a purely string-based strategy like Svelte or Markle, we'll see that virtual DOM-based solutions are usually significantly slower. But however, in the case of Vue, we have the template to virtual DOM compilation layer, and we can use the similar static content detecting strategies to optimize part of the template that can be any part of the template that can be optimized into pure string concatenations will be turned into pure string concatenations at compile time. So this significantly reduces the cost of server-side rendering because we no longer need to generate all of these virtual nodes and then iterate through them to stringify them. Everything is already strings. And the greatest part is this can still be mixed with raw virtual DOM. So you get the full benefits of being able to drop down into the virtual DOM layer and do advanced abstraction stuff while gaining performance boosts for server-side rendering for components that are still leveraging templates. So you kind of get the benefits of both worlds. And then during server-side rendering, we also have some build time optimizations by generating 2 build manifests from Webpack. So we generate one manifest for the client and one manifest for the server. And when we set up the server renderer, we can compare the 2 manifests and being able to infer the async chunks. So we first turn the 2 manifests into a data structure that's fed into the server renderer. Now the server renderer has information about both the client build and the server build, and it is able to infer the correct async chunks that's required when you initiate a request to the server. So with that, we're able to provide this meta information into the HTML template or to the server, to your raw server. So the result is we can do things like embedding async chunks and automatically generating preload and prefetch directives for the async chunks needed for a specific route. And if you set up this system correctly, you don't need to do anything manually once this is set up. Everything is automatically inferred and inline into the templates for you. So you no longer pay the penalty of one extra round trip when you do code splitting. You can just safely split every route, which is great. And another thing is we also inline critical CSS via compile time optimizations because the CSS is inside a single file view component, and we're able to convert it instead of importing the style directly. We associate the style injection to the lifecycle of the component it is placed in. This way, when a component is used during server-side rendering, its associated styles will be collected during the server-side rendering, so we know exactly which components are used, and their styles are therefore required for this specific request. This allows us to generate the minimal amount of component-critical CSS for a given request during server-side rendering. And as you can see, there is this critical CSS part, which is inlined in the final result. So this is the example request you get from the Vue Hacker News clone demo. And finally, we have something called custom modules for the Vue template compiler. So this is a pretty advanced feature, but if you want to, you can actually hook into the compilation phase of the Vue template compiler. And you can provide custom modules, and each module can transform the AST, a template AST. It can also do post transforms, like just completely rewrite the generated code. You get a lot of flexibility in this architecture. And one of the prime examples of such usage is build time internationalization. So previously, the Vue internationalization package performs pure runtime internationalization, but that comes with a cost because you're shipping the whole locale's data structure to the client, and you have to pay the runtime lookup cost. And everywhere you need to do every time you need to do internationalization becomes a dynamic binding, right? But with compile time optimizations, by injecting a custom compiler module at compile time, you can turn all the internationalization directives into purely just setting the text content. So this is same as static text, essentially. Now you completely get rid of all the runtime costs associated with internationalization, and you just generate different copies of your app for different locales. OK, so I'm running out of time, so I will just move fast here. We do some pretty interesting optimizations in weeks, which is essentially the React Native equivalent for Vue. Inside certain types of recycle lists, we generate different code so that we delegate more to the native renderer rather than spend in the JavaScript runtime. So this results in greatly improved list rendering performance. And some ideas under exploration include similar inspired by Svelte. We can remove features that's not in use in your Vue app by doing static analysis. We can compile a single file component directly into web components. This is similar to what Stencil and Svelte does. We can even do style-tron-style atomic CSS generation at build time, because all the styles inside your whole Vue app can be extracted and analyzed together at compile time. We can do minification, dedupe, and atomic CSS generation. So static analysis opens the doors for all kinds of exciting future possibilities, quoting Rich Harris. And I believe we're just getting started. I think there are a lot more possibilities. They're not specifically bound to a specific framework. So I'm really excited about this. I think everyone should explore this area. And I want to see more of this kind of experiments coming out for all the frameworks. Thank you.